Today I will cover the functions that you can use to complete problem set 5. Now I say can use because in order to complete the problem set you actually don't need to use RStudio, I believe. So I just want to show you how you could do this assignment in RStudio or answer some of the questions if you wanted. But I will say if my video or code is confusing, please don't feel like you need to watch it. Refer to the professor's lectures if this video makes things more confusing. But for those who want to check this video out, there is some answers to some of the questions. So as usual, this code that we're going over today can be found at the following link. What we're going to do right off the bat is what we usually do, is to install dplyr if we haven't already. I have. You can run it, and if you see blue, that's generally a good thing, so dplyr worked. Now we are going to tackle question 1 of problem 1. Now there is a study of HIV positive women who are randomly assigned a drug, and the professor wants us to make a table in question 1a. So we can create the table first by thinking about what our total number of people is, and that is 164 plus 160, as you see here. So if we run this line of code here, we will have this saved up here now. And the second thing we need is X, or the number of successes of a baby testing negative for HIV. So the way we actually calculate that, it's pretty straightforward. It's the total number of mothers, or total number of babies, and we will subtract the babies who have tested positive for HIV, which this data is actually up here. The numbers are up here, but I will use in this example different numbers because I don't want to just give you the answer right off the bat. I want you to actually plug these numbers in. And when you plug these numbers in, n minus the positive HIV, X will eventually just be all of the babies who have tested negative. So if we run that, you'll see that we have an X up here. And then the probability is just a simple calculation of those who have tested negative over all infants. So that's P. And so we can put all of these N, P, and X together using this cbind function. This means column bind. So it will create, cbind creates rows. Sorry, 3 columns. Columns, excuse me. And so if we run this with all that data that we've just produced here, what you'll see is the table that is necessary for your answer. Now all you need to do to get the answer is actually just swap out these 20 and 10 with the numbers up here. So you can run that all at one time, and you will then, voila, have the answer to 1A. Now the standard error calculation is a little bit more difficult, and I'll refer to my notes to show you, but this is essentially the formula. So we need to do P times 1 minus P over N. And we calculated P hat, which is a sampling proportion, beforehand, right? So that's what we calculated here, so we have that. So as a result, it's actually not that difficult to do. I chose to make a function, but I actually realized that that can be a bit confusing. So before I use a function, I will show you how to just calculate it by more or less copying what is in this formula here. So it is square root of P, times 1 minus P divided by N And what you'll notice is that it spits out the answer. And just to make it extremely clear, this is not the final answer for 1B because you need to, again, make changes here. But that will more or less give you the answer. So that's the easy version. And the difficult version, I guess you could say, which is optional, is we use a function. I introduced this last class or last video, so hopefully some of you remember. It's exactly the same thing that I did here, but it's just in different steps. So I'm going to run this function. So now I have this answer function, 1, 2, that you can see up here. And let's give us a little bit more space. And after we run the function, we can use the function. So I use the function 1, 2 here, and then inside of that function, I just put the sampling proportion and the total number, which I already calculated beforehand. And so when we run this, I don't need to save the answer. I can just show you right here. We get the exact same answer. So that is how you do 1B. Now 1-3, again, I'm using yet another function because this right here is the how to calculate the confidence interval for 1C. And so what I'm doing is creating yet another function, and the inputs to this function are the sampling proportion, so that's P right there, the z-score, which is right there, and the standard error, which is right there. So actually, I believe I need that standard error from this from 1.22 in order to answer 1.33. So let's just save that. And so again, just to make it clear, I'll do 2 versions. So there's going to be 1.31. This is the easy version. And that's just simply to calculate P plus Z. So the Z, actually, you're going to have to input yourself. So in this example, I'm going to use Z as 1.5, but this is actually not the answer. You're going to have to find the Z-score that you need for a 95% confidence interval, and I think some of you actually know that, but for this example, I will just do 1.5. So please change this. So I will do P plus Z times standard error. So we'll run that, and that's our answer down there. We also obviously need to do minus here because it's plus or minus, right? So we have 2 different answers. But the complicated version with the function, right, it's the same exact thing as 1.32, except it just kind of prints it out a little bit better. So if you can just run it all at once, it's probably the easiest. Made a little mistake there, but I will correct that. And what you'll notice is that the answer is the exact same. So I'll just run it one more time. Answer function 1, 3, run it all at once, and what you'll notice is that corresponds to this here, the first line, and then the second line is the actual answer. 1.4, which corresponds to 1D in the problem set, is actually relatively straightforward when using R. It's a 2-sided hypothesis test, and you can actually just use this prop.test function, and so in that we put our x, which we calculated from the very first problem, which is right here, and then n, which we calculated again in the very first problem, and then the we need to assess the probability that the likelihood is 25%. So we do p equals to 0.25. If it was 10%, this would be 10, or 0.1, excuse me. And then we also include this attribute of correct equals f, which I'm not going to get into, but that's how you run it. And when you run the answer, then you will want to see whether you can reject the null hypothesis. If you reject the null hypothesis, which we do in this case because the p-value is extremely small, there is evidence for the alternative hypothesis, so that the true p is not equal to 25. So that is how to answer 1D. And 1D, I believe, also asks to state the null and alternative, so make sure you do that as well. Now moving on to number 2, or problems 2, we are going to look at a poll of people. So this is the data up here that I just kind of pasted in. I created a table of this using this function here. So I will run that table to show you what it looks like. And so what you'll see is that now we have a table of that data that was given to us. This matrix function that we're using, you can just put the rows and columns and then the data, and then once you specify that, then it will output a matrix that looks something like this. And so now that we have the table, we can actually easily do this chi-squared function. It's CHISQ.test is the name of the function. And all we do is input that table that we just made. And again, we're going to use correct equals f. And then in order to get the expected values, we do $ and expected. So when you run this, then you will get the answer of what we would expect the values to be if our sample was random, right? If the ages did not have an effect on how people answered. Now, I also do this by hand, and it gets a little bit confusing. So this is, again, extremely optional. I think maybe this video is confusing in general, which I apologize for. But again, if you're having trouble and it's confusing you more, please feel free to skip through some parts. The goal is to get you to complete the assignment, of course, but this here, this optional one, is to try to develop how we actually just calculated that answer in 2.21. So when I run this code here, what I get is the totals of each row. Excuse me, the total of each row, and then down here we get the total of each column, and then right here we get the total of everything, and that is created using these lines of code here. But the way to calculate it, as I kind of show here very roughly, is the way we calculated this in 2.21 is to take the row total times the column total divided by the total number of observations. So it would just be, so in this column up here in V1, right here, where 68 is, it would be 232 times 369 divided by 902. For this one here, it would be 332 divided by multiplied by 369 divided by 906. Down here it would be it would be 232 again, but this time, because we're in the second row, it's multiplied by 533 and then divided by 902. So that's what I'm doing down here. This kind of looks complicated, but it's really just meant to extract the data up here into data down here. So what I am doing is just extracting the third row. So that's just all of the column totals right here. So I'll show you that. So it's 232, 332, and 338, as you see down here. And that's how to extract it. So this is the third row, and this is the 1 to 3rd column. So that's what this is. It just allows you to what's called subset the data, and just kind of take out the parts that you want because we didn't want the whole data. So now that we have the column sums, we also want to get the row sums. So I do that by this function here, and as numeric just makes it a number. So it looks kind of fancy, but it's really not. And so now we have the row sums. And there's probably a better way to do this, but this is just the way I did it. And now we can finally calculate what we have in 2.21 because we have the column sums, which is, as I showed you, is right here. And we can just multiply that by the row sums and then divide that by 902. So, and of course, there's two different row sums. So for one of the row sums, I'm using this 369, as you can see here, row sums number 1. And row sums number 2, I'm using 533, which corresponds to right here. And so when I run this final line of code, what you'll see is now the data has been calculated. And we can cross-check this answer with what we have in 2.21. And lo and behold, the answer is the exact same. So again, sorry if this example was confusing. Feel free to skip over 2.22. I just wanted to calculate it by hand just to get a sense of what we were actually doing. Now we will do 2.3, and that is relatively easy. It's essentially the same code that we used in 2.21, but instead of after the chi-squared test function, instead of adding this expected, we will just run this first line of code, and that will give us the chi-squared test for our data. And that test we are looking for, so the null will be that there is no evidence that age provides information about approval for stop and frisk. And so if we can reject, well, let's run it first before we see if we can reject it. The p-value, as you can see, is extremely small. And this is scientific notation, so this just means 0.000 and then this number here. And so what we can see is that more or less that number is, that p-value is near 0, which means we can reject the null hypothesis. So indeed there is evidence that age provides information about the approval and stop and frisk, which makes sense given the fact that there may be some demographic, or sorry, age might play some role in how people view policing. I guess that's what this test would indicate. So now that we have done that, we can move on to question 3, and we are going to look at some data about births on Friday the 13th. And so I actually didn't do it here, but I did it here. I'm going to just upload the number of births for each 3 of the years, and so that will be saved as this data called Fridays. And then we will do the exact same test that we did in 2.21, this expected, and that will give us the expected number of births for each day. And what you'll notice is that if the Friday the 13th has no relation with the number of births, then we would expect that the numbers would be more or less the same on every day. So when we are taking this expected value, it shouldn't, I guess, surprise you that all 3 of the numbers are exactly the same. But now we are going to add the probabilities of each day. And again, I will throw in the answer here. So what you're going to want to do is, there's obviously an equal chance of landing on any of those 3 days in our sample. And so that's how we will set the probability. And we will do the same exact chi-squared test function, but this time we will use the P attribute. So P will equal this probability here that we set here. And if you run that, you will get the answer to 3C. I don't have to write that because that's right there. So that essentially rounds out the questions that you can answer with RStudio. There's actually one more question that you can answer with RStudio, but again, this is very much optional. I'm going to introduce you to the data set that we're using in question 4. So in order to do that, you need to install this foreign library actually. So I've already installed here, so all I have to do is run this line of code and that library will be installed now. And so I'm downloading this data from online, so that's why I'm using a URL. And I'm using this read.dta rather than read.csv because this data that we're importing is actually a DTA file. DTA files are used in Stata, so some of you might be familiar with it through that. If we run these lines of code, we should now have this new data frame called df_birth, as we labeled it, and you can see that the head function can show us the first couple rows. Now, actually, what you'll notice is that the data set is exactly the same as the one in our problem set if we plot it. And so I'm just going to plot it really quickly to show you what it looks like. And sure enough, that's exactly what we have in our problem set. Now, sorry, this is a little squished, but if you make this bigger, you'll see that it's the same data set. And so what I want to show you as well, because eventually we're going to be covering this. Again, this does not have to be addressed this week, but for those of you who are still watching, the LM function below that I'm using is used for regression. So this is just the basic regression function, and it's called LM. And within that, we're going to put the birth weight. So this will be the variable that we're looking to predict, which is our y variable, and then the sigs will be our independent variable, or our x. Birth weight is our y, or a dependent variable. And then for this function LM, we are just using the data set df birth, and then these are just columns. The sigs and birth weight are just columns that we have. So if you want to check that out, you can, just to understand what we're using. I'm using this column called bweight. And so if we run that, let me clear this out just to get a better idea of what's going on. This to make it a little bigger. What you will notice is that you have this output right here. So what that does is give you the intercept and sigs. So this corresponds to beta 0, this intercept, and this corresponds to beta 1. And what we can do with that actually is to use this data to answer, I believe, question 4D. So first what I'll do is extract these data from here. So I'm going to run this again, and then I'm going to, like we were doing with the chi-square test, we're going to just put a $, and then we can also extract what's called the coefficients of the data. So if we extract the coefficients, what you'll notice is that we have pretty much the same data that we had up here. And so what I do from there is create a beta and a beta 1. Again, this looks kind of fancy right here, but all it's doing is taking the first coefficient from this coefficient list that we made and making it into a number. So that's what as double is. And so what I'm doing here is creating a beta 0 and beta 1 object. And now that you see that we have that here, which is, I think, the exact same in your data set. And now we can actually calculate the expected weight of a given baby, of a given baby, or a given amount of cigarettes that are smoked in a day. So in this example, I use 10. I think in your problem set, it's 20. So what I do is I set the number of cigs in a day, and what I do is I use that beta that we had up here. So beta plus the cigarettes that we smoke a day times beta 1, because beta 1 is actually the coefficient for cigarettes smoked a day. So these beta 1 and beta 0 will not change if you're making a calculation like this. The thing that will change is how many cigarettes a day, I guess, in this example. And so if we run this line of code, what you'll see is, let me just run it one more time just to make it a little bit more clear. This tells us right here that the expected birth weight of a baby whose mother smokes 10 cigarettes a day will be 114. So if we change this to 15, you would see a different outcome, right? You'll see that it's actually less weight as it goes up, which makes sense, right? Because we are just taking the cigarettes a day times this beta 1, which is negative. So as we increase the number of cigarettes a day, we would expect birth weight to decline, right? So that is the intuition there. Now, this is actually completely unnecessary as well, but you can do that same calculation, but just in a little bit fancier of a way, and actually it doesn't look like it works. So this was an example made for this software that I use over here, so let's scrap that and call it a day.